these two topics we covered, and we said for physical layout team or layout engineer, it's not really necessary uh, to actually understand all the details in these topics, but rather it's useful for a physical layout engineer to know the basics, what's happening inside this team, right? So similarly, today is we cover the topic of circuit design. So in this circuit design, there are two important parameters that is important to the layout engineers as well. The one parameter is called delay, which actually determines the speed of your circuit and speed of your chip essentially. And the second is the power consumption. So we are going to see the details of these two, and understanding these two parameters will help the layout engineer to optimize the layout when you run the analysis and all that. So what is circuit? We know that it can be represented as a schematic or as a netlist. So schematic, it could be a gate level representation or a transistor level representation, we know that, okay? And we can draw these two schematics, and we say that this is how the circuit is working, and we talk about its logic. Another way to represent it in terms of netlist, so we'll see in a short while what netlist is and how it is written. And for a layout engineer, it's also important to understand what netlist is, because you have to read the netlist and you got to understand that. That basically, netlist is basically a representation that tells us how the transistors or gates are interconnected with each other, and where is the input of the circuit, where is the output of the circuit, and other components. So there are two ways a netlist can be written in VLSI industry, that is Verilog. So Verilog is a hardware description language. It will describe the hardware, the way it is connected. We'll see a little bit more about that. And another is the SPICE. Each has its advantage and disadvantage, that also we'll explore. So Verilog netlist, that's used for the functional verification. For instance, I have a function, Boolean function, y equals a or b and c whole bar. So it's a logic function. So I am given a task to write a Verilog netlist to explaining this function and verify this logic. So I have two approaches: to draw the schematic in terms of gate, and to draw the schematic, or I would say circuit diagram, in terms of transistor connections. So that's how I know that I will be able to realize this logic, and then to actually implement this logic in terms of actual hardware, and to verify whether y will be this function, I will write the netlist using structural Verilog. I'll show you in a moment how we'll write that. SPICE netlist, on the other hand, they have more details actually which are necessary for delay and power simulations. So we'll see that the Verilog netlists are useful to describe the logic, but they are not necessarily providing information about how much the power is being consumed by this particular function, and what is the speed, or in other words delay, that the circuit that we will realize offers. So SPICE comes in there, which has little more detail, that actually allows the designer to describe the physics of the transistors at the transistor level, and with that the designer is able to estimate two parameters, which are delay and the power. Okay, so we'll see how. So there are few things that you need to understand as a layout engineer. So first is, we know that metal oxide semiconductor transistor, it can be modeled as simple capacitor. Can anybody tell me how we can model a MOS transistor as a capacitor? So answer is here. You can see here, this what we have is the metal gate, right here. Here we have insulator, which is SiO2, and here we have a semiconductor. So you can see that this is essentially a two plates of the capacitor, in between a dielectric. So in the capacitor you have a top plate as a metal, bottom as a semiconductor, and in between you have a dielectric. So that's how we can model the transistor, CMOS transistor, as a metal oxide semiconductor capacitor. Okay, so we know that how the transistor works. So this is the transistor now. So you have the structure. So you have, this is metal, which is gate, then you have an insulator, which is SiO2, and then you have silicon, which is the semiconductor. So this is essentially your capacitor, right? And we know that when this transistor is on, so there is a source, there is a drain, and there is a gate. So when the transistor is on, we know that the charge carriers flow from source to drain. In other words, we'll say that the current flows from drain to source, right? The polarity of electrons is in the opposite direction to the direction of the current, right? And this is how we can represent it. Now we know that MOS transistor acts as a capacitor, and we know that when it is on, the current will flow from source to drain. So now this current and the capacitance, that is current I and the capacitor C of this MOS transistor, that's proportional to the transistor width. So we already know that what is transistor width here. Transistor width,
W.
right, that is the W. You can see that it is indicated, and the channel length we already know that. So we say that wider the transistor, we'll see now this capacitance and the current, that is proportional to the transistor width. So you see here, that's the drain region, that's the source region. On top of that you have a metal or polysilicon that's acting as a gate. In between you have an insulator, that is silicon dioxide, which is just an insulator, and you have this length, and this is the width. So we see that if the width is larger, the transistor is wider. We can say that the physical size of the transistor increases if it has a larger width. Okay, so now comes to understand the topic of a delay. We are talking about delay of a logic gate. So let's say I am designing some logic, or I am showing, there are two ways to show the logic by means of gate level schematic or a transistor level schematic, right over here, as I explained earlier. So I want to understand what is the delay of this logic implementation. There is some function that I am going to realize in actual hardware, and I am supposed to understand how much is the delay linked with this particular schematic. So how to calculate that? So delay of that logic gate is determined by two factors. First is the current that it can deliver and the capacitance that it is driving. Now where is the current here? If suppose I am having this particular logic schematic, I have an input X, I am using this inverter. I know I will have the inverted output Y here. You see here there is a pulse shown here with a specific rise time, and obviously I will have the output which is an inverted form of X. Then again I am using another inverter where Y is the input to this. I have this input coming to this gate, and obviously I will have another output at its terminal. So the current, the delay of this logic, it depends on two factors. First is the current it can deliver. So finally if I have a load over here, so I need to estimate how much the current this circuit or this logic is able to deliver, and what is the value of the capacitor that it is driving. Okay, so let us understand at the transistor level. So firstly I have shown you there is a one inverter which is driving another inverter, which is shown over here by means of logic diagram in terms of gates and by means of transistor diagram. So you see this is the first inverter right here, this is the second inverter right here. So I see here at the transistor level, this is the first inverter This is the second inverter. I have an input X, I have an output Y here. This output is basically driving, acting as an input to the second inverter, and I have a final output, let's say Z, something like that, or whatever name you want to indicate here. So where is the load capacitance here? Here I can externally connect a load capacitance, and then I would estimate that output of the first inverter that is charging and discharging this capacitor. So I am saying that the current that is coming out of first inverter, that this first inverter is delivering to this capacitive load, and the value of the capacitor is known to me, right? So delay calculation depends on these two factors: how much current is coming out of the inverter and what is the capacitor that the current is driving, the value of that capacitor. Now tell me, if I don't connect a capacitor externally as shown in the color here, where is the capacitance? If I don't have this capacitance here, what can act as a load to the output of the first inverter? Output of the first inverter can drive a gates of this second inverter, which are basically a capacitor. As I explained you earlier, MOS transistor, that is metal oxide semiconductor, is basically my capacitance. So there is this one plate of the capacitor which is metal, there is another plate of this capacitor which is semiconductor, and this is SiO2 in between. So that's how I know that this is acting as a capacitor C. So if I don't have any externally connected capacitor right shown over here, what I can do is that I am driving the output of first inverter to the input of the second inverter. So the gates of these transistors, they will act as a load capacitor, right? So delay calculation depends on how much current is coming from the first inverter and what is the value of this capacitance. So I am now charging this capacitance by means of current. That charging and the discharging of a capacitor, we know this well equation, the current through the capacitance. Use here, so you see that I, that is the current through the capacitor, is given by C dV dt, which is the rate of change of voltage through the capacitance. So this logic level that I will be switching between VDD and the ground will help me to understand and calculate the delay. We'll see how. So remember this equation, the current that is being delivered to the load capacitor, which will charge and discharge this capacitor, is given by C times dV dt. So let's say if I am having this average current I that is coming out of this inverter and that is charging this capacitance C right over here. So it will take some time to charge this capacitor and also to discharge this capacitor. And when I am charging this capacitor, what is the voltage level or logic level that I am charging it with? VDD, or I would say high. And when I am discharging it, it means I am taking off
ground.
Yeah, it is the ground or logic low, right? So it is taking some time, certain amount of some time when this current comes to charge and discharge this capacitor. So how to estimate that time? So we already know that what is the relation between capacitors, charge and the voltage. For a layout engineer, you should know these formulas because when you will
Equal to Q.
yeah, good. So that is, we can see that Q equals to CV actually, right? Is it correct? Right. And we know that we can write Q to be equals to I times T. We know that. So we can write basically I times T, that is equal to C times V, and the time that we are interested to calculate, which will be given by CV over I. So this is how we can see that. So what we see, understand here, this equation I can write in this fashion. You see here what I am writing, T equals to C over I into VDD, where V is here is nothing but VDD, because that's the voltage we are charging the capacitor with and the time we have now calculated. So can you see now this delay, or we are saying that when the switching is happening and charging and discharging of capacitor with the voltage levels are happening, it is taking some time, and we have calculated that time. So that is why, and that is how we are able to estimate the delay of a particular circuit or particular gate. So how much is that delay and what it is proportional to? It is directly proportional to the value of capacitor and inversely proportional to the value of the current that the gate delivers, and it is also directly proportional to the voltage applied, that is the supply rail. So I understand that if I have a large value of capacitor, is it advantageous to have a smaller delay? No. Delay will increase if I have a large value of load capacitance. So if I am driving the large value of loads, whether it's the external capacitors that I connect here or the large gates of the transistors, if I have a wider transistor, we'll see in a moment, it means I have a large gates here. So right, see here in this diagram, if I have a larger gate right from here, so I will have a larger width. It means I am driving a bigger transistors. So that is something not useful for me to reduce the delay. And of course, if I want to reduce the delay, I want to increase the current. If I have a higher amount of current that is coming out of the circuit, I am able to reduce the delay. Also, a smaller supply voltages. Nowadays, we are working with the technology which is process node of 10 nanometers and so on, and even below. But what about the supply voltages for those technology nodes? It is about 1 volt or even less, right? 1 volt, 1.2 volt as compared to 5 volts. I have explained to you that earlier. So delay will increase with the load capacitance and delay will decrease with the drive current. And transistor width will determine to meet the delay requirement. So if we want to make the circuit speedier, we want to make it work faster, whether it's in circuit design or in the layout, we want to minimize the delay. So what basically option we have is the make the transistor wider. If we make it wider, what will happen? It will have a large amount of number of charge carriers, so it has a larger current capability. So larger current will help us reduce the delay. Second option is to supply voltage should be down as low as possible. And third option is the value of the load capacitance that can be reduced. Now what about power? The first thing we understand how to increase the speed of a circuit at the logic level and at the transistor level. Second constraint here is the power. So let us understand what power is, what are the types of power. This is also very important parameter for a circuit designer and as a layout engineer. So power is basically an energy that is required to charge and discharge this load capacitance over here. So when the switching is happening, the capacitor is constantly being charged and discharged. So some energy is being supplied to it and is taken out of it. So this switching action, because of this switching action, the energy that is taken out or thrown into this capacitor is basically called as dynamic power, and this power is consumed and we call it dynamic because there is a switching happening here. So this dynamic power is consumed when the capacitor and is charging and discharged at a specific frequency. So as I've earlier said to you, X is the input. So I am showing here a simple pulse, but what about what if I have a square wave here that is changing the logics between logic 0 and logic 1. So I am having the switching waveform coming as an input and the circuit is inverter, so output will also be alternative square waveform. So it has some frequency because it's a square waveform and with the on time and off time. So I know what is the frequency of that input signal, and because of that some dynamic power is being consumed. And how to calculate that power? Here is the equation. It is equal to the value of the capacitor that I am driving, square of the supply voltage and the frequency at which the circuit is operative. So I know that if I want to second uh, purpose of the designer would be to reduce the power consumption. Two task of a designer is to reduce the delay and reduce the power. So how the dynamic power can be reduced? Obviously again have the lower value of C, but sometimes it is fixed because you have to drive a certain amount of load. The value is fixed either by the external specifications or the next circuit that is connected to the first circuit is already there. So you basically are driving the second inverter by this first inverter, and whatever the transistor widths are here, transistor length and widths, that will give a physical size of these transistors, that is fixed. You cannot change that. You have to have that load, right? So basically that capacitance can be calculated. So that is fixed. Second, square of the VDD. So the most important, we see that higher the supply voltage will have higher the power consumption, and that's why when in the modern technology today, when the scaling of the transistor is happening, or when we are talking about nanometer dimensions technology node, it also means supply voltage scaling is also happening, because for a 1 nanometer transistor you cannot operate that transistor with the 5 volt. You have to use a 1 volt or even below. So you see the voltage scaling happens because of today's transistors are consuming a very low power transistor, and hence we say that my chip is high speed and the low power, ultra low power. So that's why our mobile batteries are longing all day and all these things. So this is the way scaling of the voltages are happening right here. So square of the VDD. And third, if the switching happens faster, it means if your circuit is speedier, then power cannot be that low. So you see now, if the speed of the circuit increases, power also will increase. So remember this equation, even when you draw the layout and do some physical verification, you need to know this equation. Sometimes it will help. So what about, we saw that if the gate is switching, there is a power called as dynamic power, because we are charging and discharging the load right here, whether it is external load or the capacitance that is offered by this circuit, next circuit that we are driving. Is there another power if the transistors are not working at all? We just say that they are idle. So another power or another energy we call as static power, right here. So let's understand what the static power is. So if the transistor is off, because an off transistor is leaky. Why it is leaky? Why it is leaky? So you see here now, because of the scaling, there are many adverse effects. They are called as scaling effects that happen. So you have this metal oxide, and this is semiconductor, this is SiO2, and this is your metal or polysilicon. So basically you have this MOS capacitor right over here. So this is your metal, this is SiO2, and this is silicon. So this is your MOS capacitor, and what we see here is that you have this gate terminal. So what we see is that there is some leakage that is called as through the dielectric. So the current can still flow. It's also called as tunneling effect, where charge carriers, where when you deposit charges on the top of gate, they can penetrate through the insulator and go inside the silicon. So that is adverse effect. So this basically, this effect is more and more pronounced because of the scaling effect. In the modern transistors, this effect is to be addressed and is also challenging to address, but still we are managing with the material science to get rid of this effect. So look at here, I have a logic 1 applied here, and output of the inverter circuit is logic 0. But now when I apply logic 1, NMOS in the bottom, pull down network is on, but pull off network obviously is off, right? So this circuit is basically can be represented as I have this VDD and this is PMOS, and I would say that this transistor is switched on and this is output right here. So I see that this transistor is on, okay, but there is a static current I'm getting here from VDD to the ground. Why? So in addition to the main current, because of the switching of the NMOS, I am having the current that is called as dynamic current, and the power because of that current will be called as dynamic power. But now this upper transistor is off, so because of the gate leakage there is a current. This transistor will also be slightly on, and there is a current flow from VDD to the ground. That current I call it as a I static. So remember, even when the transistor is on, there is a certain amount of current, very small, but will flow. That is called a static current, and because of that there will be a static power dissipation. How to estimate that power dissipation? Obviously power equal to current into voltage. So you have the VDD and you have the static. So the purpose of a transistor fabrication or designer is to reduce the static current, but it is inherent there. Designers cannot do much because that's the job of a foundry and all the physics level, but you have a smaller supply voltages nowadays. Like I explained, you are operating the transistors of 1 nanometer or 10 nanometer with a 1 volt or even down. So the power, static power is also controlled or minimized. So the designer's task, even the layout engineer's task, how to optimize the two, that is delay and power. We want delay to be less, we want power to be less. So let's say I want to realize a particular logic function, y equals a or b and c whole bar, whatever. So how to realize this function? What are the ways? We have seen that there are ways to realize using compound gates or using tri-state. You should know this, right? You should know these answers because these are common questions that might be asked. So we know that, okay, there are many ways to realize, and we know that tri-state approach is compact because it uses less internal wires. Also it has a less delay problems because we know that it will be a speedier one because there are not many stages of logic level reaching from input to output. So the question that we have been asking in last many sessions, this function, should it be built with AND gate logic, OR gate logic, NAND gate logics and NOR gate logics? So we know that there we have options, and we have also understood that if we know that we can realize this. Let's say we have 2 input or 3 input NAND gate, NOR gate. This is what. So we know that we can. What about we want to implement the OR gate? We know that we will first use the NOR gate and then put an inverter. If we want to implement the AND function, so first we'll implement the NAND function and then we'll put the NOT gate there. So we know that. So then there is one more parameter that the designer takes into consideration: fan in and fan out of each gate. So there are logic gates right here. We'll explain them in some other sessions. Today we'll not talk much about that. Fan in, fan out. This is just a digital logic concepts that a digital designer should know. But we'll see if they come across and if we are in need to understand them in detail. But then next question during the circuit design is how wide the transistor should be, right? So we know the width of the transistor, and we know that there is a length of the transistor that we'll see. This is the length and that's the width. So we have to consider all these parameters to minimize the delay and the power. We have understood what is delay, what is power, and how to minimize them. So all these choices above, so we know that whether to use compound gates, tri-states, whether to use the logic, implement the logic using NAND or NOR or AND and OR, what is the transistor width, etc. So all these choices will affect 2 factors. First is capacitance. and the current in the circuit. Because if we use the wider transistor, will the capacitance of that transistor will increase or decrease? If I am driving this circuit to this circuit, these are the having wider ratio, let's say W by L of this is 1, W by L of this is 1, and there is ratio of this is 10. So which transistors of the inverter are larger or bigger in size? The second, right? Because I have a larger width to length ratios. So what I know is that the capacitances, the MOS capacitance, because they are acting as a MOS capacitances to this first circuit, they are acting as a load, even though I don't connect this external capacitor here. So they will affect the capacitance, and if I have a bigger transistor in size, it will have a large capacitance, and obviously it will carry more current. And because of these two factors, speed and power of the circuit will affect. So if the speed and power of the circuits will affect, it will affect the area and the cost of the chip. Because we are talking about one simple circuit. This is a standard cell of CMOS inverter. We have millions of such cells in an IC that you will ready-madely use using your tools. You will place them and you will implement your logics. You will implement your logics, then you will use those logics to implement the bigger logics, or I would say the functional blocks we have seen. Then you will use those functional blocks to implement your architecture, micro architectures, and then we upper one more level, hence you will finish your final architecture of the chip. That is called a system on chip or application specific IC, that is ASIC, right? So can anybody tell me now if the capacitance and the currents, how they are affecting the speed and power again? One more time. How capacitance and the current in a transistorized or gate level circuits are affecting the speed and power of the circuit, and therefore the area and the cost of the chip. Anyone? This is crucial to understand this point. Or did you understand what I explained you so far in these slides?
Yes, yes, sir.
Yeah, so can anybody just recall and revise, tell me how these choices, like I said, we are using compound gates or tri-state, and we also know which, like, so tell me what is the capacitance and current?
Basically, delay can be determined by two factors: the current that can deliver, I mean the current it delivers, and the capacitance that it has, the load capacitance. If the capacitance is greater, then and then it will consume, then the delay will be a lesser. Why? Because the current that it goes through that capacitor will be greater. Greater the current, the lesser the delay. And the small. One more thing is the VDD voltage. If the VDD voltage is lesser, then it will help reduce the delay.
Right. So capacitance should be smaller actually to reduce the delay, and the current should be larger, right? Did we see that? Because this is the delay time. This is the delay, right? So you see this relation, capacitance should be smaller, that it is the current is driving, and the current should be wider.
So with increasing load capacitance, the delay increases, right?
Right. So if the load capacitance are kept small, the delay will also reduce. And if the current transistor is wider in physical size, it is bigger, then the current will be more and the delay will also come down. So with supply voltage also smaller, the delay will come down. Understood?
Yes.
Okay. So how, like I said, we have we got this understanding uh, by analyzing this simple cell. We are calling this as a cell, but there are millions such cells now. As I said, that's what is making the application specific IC, or we call it as a system on chips. So we are using the standard cells, and each has we have seen the switching actions, and we understand delay and power. We know the equations now, and we also got the few points, crucial points to understand how to optimize, basically how to reduce them. So tools are there, obviously. So the first tool is the logic synthesis tool. So this is again the tool of a logic designers, and of course the circuit designers. Designers and the circuit designer. So they are different teams, but they are highly interdependent. They are always coordinating with each other. And the third team, physical design or physical engineers, they're all interdependent, as I said before. So logic synthesis tool for the first two teams and the team of engineers, they have access to this tool, and that is their tool name is logic synthesis tool. These tools will automatically make all these choices. What are those choices? Particular logic function is implemented by the circuit designer or a logic designer, and then he or she decides to go by a compound approach or tri-state or any other logic, and he know that there are two ways to show the logic: circuit way or logic gates way. And then he has his own knowledge, experience, accordingly he wants to implement. The next question he has, which cells, standard cells, he has access to the library of these IPs. They are called as IP cells. You can note down these points, very important. Intellectual property cells. So he will choose which IP cell can be taken out from the library, can be called upon from the library for the implementation of the logic he wants to implement, whatever the logic that could be. Then fan in and fan out, as I said earlier, another point. And then he will also think about what the transistor is. And we also see that all these choices above, 1, 2, 3, 4, they all will affect the capacitance of the circuit, current in the circuit, and therefore speed and power of the circuit, as well as area and the cost. So essentially it is applied to the whole chip, where millions of IP cells are operating simultaneously or in part. So the tools that the designer will use, automatically the designer will let the tool automatically decide this. The tool is so advanced nowadays that the tool will make these automatic choices, and the tools will search through these standard IP cells for the best implementation. For example, like is shown here, it will define the input output, because we have the logic designer will already write the netlist using the structural Verilog code. We don't need to understand how the code is written and all these things, because that's a different topic, but we just need to know what is happening in the logic design team and in the circuit design team. So they define inputs and outputs, they define the clock, they define some time constraints, they define some power and delay. Power and delay optimization will be taken care by the logic synthesis tool, and this is the automated diagram that will be generated. So circuit design is done. So basically it's called as logic design, that is done. Next step down this is the transistor level circuit. So for many applications nowadays, when the chip is being designed, the library of IPs are available. Usually that is foundry provided or custom made, and synthesis tools are very good and fast enough and efficient enough to automatically generate this. But for the critical requirements of high speed or low power requirement or large volume, you have like ASIC or system on chip. So all or many of the blocks you are taking the help of logic synthesis tools, but there is some portion that is called as custom design. So it's not automated for this particular block or logic or architecture or micro architecture, where high speed and low power, or if this SoC is to be fabricated in a large volume, there will be a thousand, several tens of thousands of such chips that are required to be fabricated, and there is some critical requirement of optimizing delay and power. Then custom circuit design team, this team will focus on the optimization of this particular block, because optimization of this particular block will optimize the whole chip in terms of power and the delay, right?
So I have a small question.
Yeah.
So can you go to the previous slide? Where does in the logic synthesis, where does from where does the logic synthesis team get the technology library file? Like, do they get from the physical design team?
Repeat your question again.
For converting the behavioral code to the gate level netlist, from where do they get the technology library file?
That is installed in their tool set, that is called as PDK, process design kits. So they use the tools in their set of tools. Their set of tools are different. Physical layout engineer set of tools are different. So in their set of tools, that library is already installed, that PDK is already installed, and from that they will use the coding. Then using the EDA, they will compile. So that tool, they call it as a compiler. When they compile the code, is basically a simulator that will perform the verification of that logic they are designing. They will analyze, then the tool will display the set of waveforms. For example, it's a latch or flip-flop, for example. Then they will analyze whether that logic, what they want to implement, is satisfactorily and is behaving the way they want. After that, they will apply and invoke another set of tool, which is a synthesis tool. Then that tool will take the netlist from the compiler tool and automatically generate this figure. So it's already library of these functions to do this task is already defined in their tools. It's already installed. For example, they are using the 22 nanometer technology in which they want to implement this logic.
Okay, that will be the technology library file, whether it will be 20 nanometer or 5 nanometer.
Right. But that is not much relevant when they are implementing this task. They know that in which technology they are already working.
So with the help of that technology library, they are able to report the area, power, and whatever. Yeah.
Correct. Good question. Yes. They will
Thank
estimate.
you.
The tool will actually calculate them for them, and they will then generate the report. Yeah, the tool will generate.
Got it.
Okay. So we are coming back to the again the slide where we talk about optimizing the delay and the power. So as I said earlier, circuit design team, they always draw the schematics in two ways. First is the gate level, by which they can just see the inputs outputs of their systems and the outputs, and they analyze the diagram. Second is transistor level design. So this two circuit designs schematics, they are basically representing a simple carry circuit in a full adder. So I hope you in your studies or in your colleges you understand the working, what is half adder, full adder. So full adder, it generates the sum and the carry. Sum is SUM, carry is C out. So these are the two basic representations. So I'm not explaining you the working of how full adder works here. It's just like what circuit diagram understands. So for many applications, as I said, synthesis tools are enough, and critical requirement of these two circuit, we'll see how these two circuits can be implemented and optimized for delay and power. So the first gate level design. Can anybody tell me that this is the gate level logic? We have to estimate how many transistors will be required and how many stages of the gate delays in this particular gate level design. Hint for you is here. We know that hint, ANDs and OR logics, they are always built from NANDs and NORs followed by inverters. We know that, right? So that's your logic. Tell me how many transistors will you take as a circuit designer, and once you implement, what are the stages of gate delays?
So normally it will take 16 transistors to build such carry out circuit, but why does it take? How does it take 10 transistors? Like how they optimize to the 10 transistors? That's the question that I'm getting.
No, my question, first answer my question. A simple question I have put forward. How many transistors? We already know, we have already done this exercise. There is a logic function given to me, and now I am asked how many transistors I need to implement this logic. We can use
16, sir.
Okay, 16. Anybody else? Simple, is very simple. You already have done, those who have done the exercises and understood the previous sessions, they can quickly should be able to figure out by just hint is given to you. You know what gates they are. You know the input outputs. Yeah, try at least others. Just tell the numbers, because these are all questions that you should know the answer about, or if you want to get some positives from the industries. Because after circuit designer, this team is going to hand over your team to draw the layout for this. So even if you will use the PD tool sets that you have, and the layout will do it automatically for you, but you should understand it. So unless you understand what's happening in the circuit, it's difficult to understand the layout. Are you following me? Are you with me?
Yes, sir.
Yeah, unless you understand what's happening here, tool will do it for you, no problem.
Okay.
Sorry.
What?
8 minutes. Sorry, Mr. Radha.
Yeah, at least try. Recall your previous knowledge and sessions that we have taken is easy, and this is important for you to understand delay and powers in a logic design and in a circuit design, and therefore this directly comes to your team, layout design. So 16 transistors somebody said, right? How? So I know that hint is ANDs and OR, they are built from NANDs and OR, I know that, followed by inverters. So I know that if I want to implement two input AND gate, A and B and C, so I will go for first NAND followed by inverter C. So what is this? This is first AND gate, two input AND gate. This is gate 2. This is gate 3. So I want to implement this. So each implementation will take this form. How many transistors I need to implement the NAND logic, to input NAND logic? 4 transistors. I know that there is a pull-up network, there is a pull-down network. Pull-up, pull-down. Output of this goes to inverter. Again pull-up and pull-down. And final output. So this is the NAND logic, this is the inverter. Are you recalling with me? VDD, this is ground. So 2 transistors,
Yes, sir.
4 transistors for the NAND and 2 transistors for the inverters. So total 6 transistors I am going to require to implement gate 1. So 6, 18 transistor right here. And now I have to have 3 input OR gate. This is OR logic, gate 4. So I know how many transistors for this? 3 inputs. How will I implement OR logic? I will first implement the NOR logic, 3 inputs NOR logic, A, B, C. So that's NOR logic followed by inverter. Simple. So how many transistor I need here? 6 transistor plus 2, 8 transistor, right? So 16 plus 8, 26 transistors are needed. Yes or no?
Yes, sir.
Right. Now tell me the how many stages of delays from input to output. That's also important question. Again, think carefully. Don't look at this. This is not the too simple because I cannot have a direct implementation of AND. I need inverters here. So it's basically I am drawing this circuit. So first, then second, then again here, third, and then fourth. 4 stages. Are you following me?
Yes, sir. Yes, sir.
Right. So 26 transistors total, transistors, and 4 stages of delays. Obviously, the speed will see. But now the same transistor level design with some circuit design technique somebody has implemented. How many transistors you see here?
Well, I think
12 transistors and stages of delays. Is the first output here of this circuit.
5.
And then this feeds to this circuit and this is the second output. So 2 stages of delay.
Sir, could you please explain once more how that stage is made? How we
That's
can
not
find that?
Sorry?
How can we determine the 4 stages?
This upper level
Yes.
circuit? Yeah, so
Yes,
this circuit I know how to implement this. For instance, this is the circuit, and if I explore more, if I simplify this, I know this circuit will be implemented like this. I have A, B, get 1. No, I will not call it get 1, but this is how I will call X. So you see X comes here, right here. Then I have A and C. Then again this comes Y here, this Y, and same B and C. That's Z. And now what about this 3 I have want? So I know that OR gate. So first I need an OR gate. So that is, and this is my C out right here. So how many stages? So first output of the circuit is here. So this is the first stage. Output comes here. Then inverter passes through it, passes through inverter. This is the second. Then this passes through the NOR gate. This is the third. And this is the fourth.
Okay, sir. Then what about the second figure?
Yeah, second figure, So circuit designer has implemented, this is the circuit for carry circuit in a full adder. So you see here, we see A right here, then you see you have a B here. So you just see that the way transistors are connected. That's not important how he implemented that. What we want to see that total number of transistors required. So we counted them to be 12 transistors. Somebody told me that, right? We can easily count them. What is looked, because this is the gate level. So we wanted to understand what is inside, how the transistor circuit will look like. But now here already a transistorized circuit, so we can easily see that there are 12 transistors used. And what is the we know that there are the inputs to the gates. Where is the output of, this is the first output that is coming at this stage, which is feeding this second stage of the circuit, and then this is the second stage. So two stages of the delay. You can just interchange the position of the transistor to understand the two output.
So,
So how is the
First,
reduction done?
this is the second. Yeah.
How is the reduction done from 4 stage to 2 stage?
Yeah, so that we have to then understand how this circuit works, the operation of the carry circuit. First, we need to understand the operation of the full adder. I will encourage you to read how the full adder works, and then sum and carry, how that obtains. Once you know that, you will be able to understand how to create the logic diagram. And even we can then, once you know the logic diagram, you can create the circuit diagram using transistor compound gate or tri-state approach. That is one thing. This, I would say, some innovation in the circuit design that we will need to understand the operation, right? This is optimized circuit, some IP, intellectual property, I would say. But if you apply the inputs and you know how the sum and carry is obtained in the full adder, then you can understand how this circuit will work. Again, you apply the logic 0 and 1, and if you know the operation of full adder, then you come at C out, how the carry is obtained here.
Is there any method like in the digital circuits we perform K-maps to perform reduction? Is there any similar method in this to
True,
perform
true.
reduction?
Yes, yes. Like you can, yes, circuit designers and the logic designers use this Boolean optimization, K-maps, to reduce their logics. But that is the job of mostly a logic designer team who just does the coding. But like I said, when you do the functional behavior, for instance, you write the full adder code, then you will write the behavior. There are two types of codes: behavioral description and structural description. So behavioral is just telling the, it's just a blank box. It tells that, okay, implement me or give me a circuit and behavior of the full adder. So I have A, B and C input and C output, and the synthesis tools will take care of it. It will just take the IPs from the libraries and it will implement this logic on its own, because I have just described the behavior as a logic designer. Structural,
Just
I will mention what, through the netlist I will mention what gates the tool has to choose, what logic functions it has to choose to finally implement the full adder. So it depends on what we describe. Was that your question?
That's a little bit relevant, sir, but that optimization is done by the tool itself, like the synthesis. Whoever performs the synthesis cannot perform this minimization through paper, through hands-on paper method. That's what I'm trying to ask. Like in the digital circuits, we perform optimization using the K-maps, right? But in the transistor level, like converting those gate level, gate level netlist to the transistor level, how do they perform it? That's the question. Like, what technique do they use?
From the gate level to the transistor levels, right?
Correct.
That is also a good question. Let me think, because I explained to you, once they define the code, the logic synthesis tool will automatically generate, take the IPs installed in the library to implement the synthesized diagram like I shown here. You see the logic gates and all that, right? So whatever the logic gates they have used here, the tool automatically generated. Same fashion, there will be a circuit design IPs also already installed. So if it chooses a NAND IP here, NAND IP or NOR IP, so the circuit level implementation is already also there inside that library. So accordingly, the tool will take those IPs for each gate, and then interconnection will be done automatically. This is what I think, but maybe I have to check again once again. uh, if there is some additional information I can provide to you.
Got it, sir.
Okay, so we've seen that. So how people optimize delay and power. So for instance, there is a gate level design and there is a transistor level design. So for instance, if you let the tool do it, almost all tools are automated and advanced. They already know how to choose these logic gates, and hence the transistor level design for optimizing delay and power. There is no further scope for a given technology, and that's how they will estimate power and the delay. The tool will generate the numbers. Again, if you want to again optimize delay and power, then I would say that's the subject of a research. In a research technology and research environment, people go for this further implementing and innovating the transistor level design, because you will implement at the gate level or the transistor level. They will innovate, so they come with the research ideas, and accordingly you can optimize delay and power. But usually, yes, to coming back to your question's answer is, the tool are so automated and advanced today that they already generate the logic diagram, and hence this circuit, in fact, when you are generating a logic diagram, essentially you are generating a circuit diagram, right? Because when you put after the logic synthesis tool, when the netlist is generated by the logic design team, the gates are synthesized. Whether gates, you call it as a gate level design or transistor level design, because inside the gate there are transistors, so it's already automatically generated by the tool. That is then either dumped into the FPGA or sent to the foundry or sent to the physical team. Understood? Yes or no?
Yes, sir.
So there is one more approach, like I said, for in the logic design term, structural Verilog HDL. So what is structural Verilog? I know it's just a hardware description language. The schematic, whether it's a gate level, they netlist it. Netlist it means they want to describe how this structure working. So it means they call one word. You can also, physical layout team will also use this netlist. What is netlist? That netlist is a description of how these logic gates are connected. It's just a C or C language program similar to that. It's not that program. So similar program. So you see, for example, they define which module they are designing. Module, carry circuit. This is the carry circuit. So they define input logic and the output logic, A, B, C. Output logic is C out is the output. Then X, Y, Z is the intermediate logic. Then say use AND gate, use AND gate, use AND gate, and then use OR gate right over here, and then AND model. So this description, code level description, is called as netlist. So this is technology independent structural description. Because why technology independent? Because we are not telling the tool which specific gates or which specific things they have to do. For instance, we are not asking the tool to optimize the circuit for delay and power. We already know that it will generate the optimized circuit for in terms of delay and power. So the tool will use the generic gates or common ITs that is already installed and which are advanced also in that technology node. So generic gates will be used as defined in this code, and the actual gate implementation we haven't specified. So we know that these gates, we already know that as a designer they have to be implemented by compound gates or tri-state gates, and we know that to implement AND and OR logic we use NAND and NOR functions. So we don't specify that use specifically NAND and NOR, so tool will determine. Another netlist is transistor level netlist for this another circuit. So transistor netlist, it basically a description of how the inputs and outputs of these transistors are defined. So you see here it looks like that. So it's not very important to understand at a deeper level for this Verilog hardware description languages for a physical team, because as I explained earlier, that's the job of logic design team. But just for a sake of understanding, let's see how these things are defined. Again, we are talking about designing a carry circuit. So module carry, we say that input logic is A, B, C, output is defined as try. It's just a simple name. And what is that name? C out. So try is I1, I2, I3, I4 and Cn. Where is that? You see I1, with just a fashion the way it is defined. I1, that's the node here. I1, I2 up to I4 and Cn, they are the nodes. Nodes means the points in the circuit, the points in the network where the voltage levels will switch between logic 0 and 1. Then we define the supply 0 and VDD right here. Then the transistors are defining. So you just say instead of tran if 1 N1 or tran if 0 P, P1, P2, P3 up to P6 or N1, N2 up to N6. So N indicates it's NMOS. Tran if 1, it says it's a name of the transistor. You can simply write NMOS, N1, NMOS, N2, PMOS, P4, PMOS, P3, something like that. So it's just a way it is defined. Where are the N1, N2? Right here. You see N1, N2, N3 up to N6. Again same PMOS, P1 up to P6. And what is in the parenthesis? It shows the connection as drain. First node is drain, source and gate. It shows the first transistor I am calling is tran if N or simply NMOS. The name of that is N1. It is indicated by N1. And its drain, source and gates are connected to the nodes I1, ground and A. See here, N1 is a NMOS transistor because it is N1. And its drain is connected to, the drain is connected to the node I1 right here. The gate is connected and the source is connected to the ground and the gate is connected to A. So I'm just describing through the netlist all its terminals where it is connected. Same I follow for all the transistor and then end the module. So again I define the module, what circuit it is, it's a carry circuit, what its logic is, input, output, supply voltages and the transistor, I end it. So as a physical engineer, this netlist will come actually. That netlist physical team uses to generate the automatic layout. We'll see that in the next section.
So I have one question. Is this netlist technology independent?
No. Yeah. This Verilog HDL, structural Verilog netlist, is technology independent. Good question. But when we go for implementation, tool knows which technology it has to implement. It's a good question, yeah. But there is another netlist called SPICE. That is technology dependent, because there we actually will see how that netlist is defined.
So basically, this netlist also goes into the synthesis tool, right? With the SDC and the technology library file. The netlist
Yeah,
that we are
yeah,
seeing
yeah.
here.
The synthesis tool, when the code is given, such kind of, not this code. This is the netlist, okay? For instance, this code is given to the synthesis tool when we write the RTL or Verilog code, structural or behavioral. The tool, first tool we'll use is a compiler. They will compile it, just like using C language, we use C compiler. Then it will generate the timing diagram for that particular logic. Then designer will analyze whether what logic I have designed is working. Is it that logic or another logic or some error? It checks for timing and all this. Once it is satisfied, then it will invoke synthesis tool that will use this description to generate, automatically select the IPs, as I said, automatically select the generic gates or the specialized gates, depends on what command we give to the tool, and generate the synthesized diagram, which is shown here, this one. And with this itself, it also will generate the transistorized diagram. With this, it always with this it will also generate the netlist right over here.
Okay, so basically the netlist that we are going to get will be the gate level netlist as well as the transistor level netlist,
Yeah.
right? Okay, so but in this one, in this case, we already have the transistor level modeling, right? So will it produce the gate level netlist for this file, or it will produce only the transistor level netlist for this file?
Good question. Again, good question. So if you describe the structural, if you use the structural Verilog to describe your to write a code to describe your transistorized circuit, as in this slide, so it is producing this netlist, and it is the transistor level netlist, and the earlier is gate level netlist.
Okay, yeah, got it. Thank you.
All right, so that's all for today. We stop here, and there was some question about what tools are used in the industries yesterday. So there are many tools actually from different vendors. You can see here there is Prime Time, Graphics, Ashura, and so on. So we'll see how these. Yeah. Any other questions? So if not, there are no questions. We stop here. Okay.
One question, sir.
Hmm.
Since there is course for the PD and the DFT and others, what will be the course for the one who is going for the logic synthesis? Is there any specific training for that? Or that's my relevant question, sir. Like the PD and the DFTs are there, then for the logic synthesis, does it require anything?
Good question. Another good question. So we offer one course is called as RTL Design and Verification, where the trainees are taught the coding in register transistor logic, that is RTL, using Verilog and HDL. Then we teach them how to write the codes, behavioral and structural, use the tools, compilers to simulate, analyze timings, and that course also consists of the understanding of the synthesis. So that's the description, brief description of that course. So this the name of the course is RTL Design and Verification. And one
So
more
that
point
comes in
is,
the front part only, right?
yeah,
Front end.
and that is the most easier to get, most easy course I would say, in my opinion, to get the job to make an entry in the VLSI industry. This physical design and that comes in the back end later.
Got it.
Any other questions? Okay, if there are no questions.